Welcome to the demonstration of Replay with Recomposition, a tool to perform alignment-based conformance checking through a divide and conquer strategy. Given a process model and an event log corresponding to the process, the tool aligns each trace in the log with the closest matching path permitted by the model. Through this alignment of the log trace and model trace, deviations between the model and the reality as observed by the recorded events in the trace can be pinpointed at the level of activities. For example, using an alignment, we can identify an activity that was executed in the log but is actually not permitted by the process model. As we will demonstrate later, such detailed deviation analysis can prompt further actions to improve the process. Due to the performance issue of the existing state-of-the-art alignment algorithm when applied to larger and more complex processes, Replay with Recomposition decomposes the model and log and aligns the decomposed subcomponents separately. Afterwards, alignment results from subcomponents are merged as an overall result. This divide and conquer strategy has shown to give significant performance gains in terms of both computation time and replay feasibility over the non-decomposed or monolithic approach. Furthermore, in the previous work we have shown that this merged result corresponds to the exact overall result that would have been yielded without decomposition. In this demo, we'll go through the complete process of importing a process model and log to getting the final alignment results computed by the tool. To apply the tool, a process model denoted in PetriNet and an event log formatted in Access are required. In this demonstration, a synthetic dataset is used. Both the model and log are generated using the PLG process simulation tool. After importing the process model and log, we can find the plugin called Replay with Recomposition. Currently, two versions of the plugin are available. One is where the users can configure the parameters for the framework, and the other uses default configurations for the parameters. For this demo, we would use the configurable version. The Replay with Recomposition tool is highly configurable with the goal of balancing result accuracy and computation time. The configurations are three main aspects. First, the user can select how decomposed replay is to be performed. Second, termination and trace rejection conditions can be configured. And third, users can configure the initial decomposition of the model and log. We first configure how decomposed replay is to be performed. Here, we can select a classifier that maps events in the logs to transitions in the model. And on the right, we can see a visualization of the PetriNet model. Alignment-based conformance checking is a cost-based algorithm, such that costs are assigned to moves where each move is composed of a step in the model trace and a step in the log trace. Here, costs can be assigned to log moves for which the step in the log is not followed by a corresponding step in the model, and model moves for which the step in the model is not followed by a corresponding step in the log. Different decomposed replay methods can also be selected in the tool. One can choose the hide and reduce decomposed replay method or the default original decomposed replay method. Next, we can see the mapping between transitions in the model and activities of the log. If the classifier has been chosen correctly, transitions should equal the activities. Now we move on to the configurations for termination and trace rejection conditions. The goal of these parameters is to allow users to configure the balance between result accuracy and computation time, We first look at configurations for trace rejection conditions. The overall computation time can be substantial if traces incur many conflicts when their alignment results from decomposed subcomponents are merged, or if they take a long time to align. Here we can adjust the maximum conflict threshold and the trace calculation time threshold so that traces that surpass these thresholds are rejected and will not be aligned. While rejecting traces that are difficult to align will reduce computation time, this will sacrifice result accuracy such that an approximate result will be yielded rather than an exact result if traces were rejected. Now we can configure the termination conditions. Other than generic parameters such as overall calculation time and the alignment percentage threshold, one can also set thresholds for the result accuracy related to the fitness interval and the maximum number of replay iterations. Lastly, the initial decomposition of the model and log can be configured by selecting activities that are decomposable. For simplicity, leaving all activity decomposable would give a maximal decomposition of the model and log. For this dataset, replay with recomposition takes around 2 minutes to complete. If we were to apply the non-decomposed monolithic algorithm, replay would not be finished even after 1 hour. Following the completion of the replay, conformance results can be analyzed under different lenses. We look at the two most used visualization. First, we visualize the alignments of the traces in the log. Green arrows correspond to synchronous moves where the model and log are fitting. Gray arrows correspond to invisible moves. Purple arrows correspond to model moves, and yellow arrows correspond to log moves. Here, we can select a model move on activity G. We can see a model move on activity G and a log move on activity G. This suggests that there is a discrepancy on where activity G was executed for the model and log. Aside from alignments of traces, the fitness score for the model and log is also shown on the right. Out of all the indicators, the most important two are of the fitness interval, denoted by raw fitness percentage low and raw fitness percentage high. A fitness of 1 means that the model and log are perfectly fitting. Here we can see that fitness is quite high and that the two bounds are both at 0.99, which means that the exact overall fitness was computed. If traces were rejected during the alignment process, the two bounds would be different, and the fitness interval would correspond to an approximation such that the exact fitness value is within the interval. Other than visualizing alignments of the traces, the alignment results can also be projected onto the model such that the problematic transitions are visualized. Here we can quickly identify the problematic transitions, activity G and activity I by the error bars. The error bars shows the ratio between synchronous and model moves. For activity G, we can see that there were 74 synchronous moves and 145 model moves. And for activity I, there were 145 synchronous moves and 74 model moves. In a real-life example, identifying these problematic transitions would prompt further investigations to the causes of their occurrences. With that, we have demonstrated how to use the tool Replay with Recomposition to perform alignment-based conformance checking in a decomposed manner. Thank you for watching and hope you have enjoyed the demo.